fundamental topic, which is sorting. And we're going to start with the insertion sort algorithm. Sorting is used all the time, and there's a ton of different sorting algorithms, all with their own trade-offs. It's usually applied to arrays like this one, but you can also apply it to other data structures, including linked lists and others. So in this case, we have an array of 5 values, and clearly they're not in order. They're not in ascending order, which would be in increasing order, like 1, 2, 3, but they're also not in decreasing order, which in this case would be 6, 4, 3, etc. Suppose we want to sort them such that they are in ascending order. So our target array would look something like this, 1, 2, 3, 4, 6. We can achieve this with the insertion sort algorithm. Let's see how we can do it. Well, the main idea is to break the problem into subproblems again. So if we want to sort the entire array, the first thing would be to have the first portion of the array, meaning just the first element, have this sorted. Well, one value, like 2, is sorted by default. I mean, how could this be not sorted if it's just one value? So we consider any array of one value to be sorted. The next thing to do, the next subproblem, would be to sort the first 2 values. Make sure these are sorted, and then have the first 3 values sorted, and then have the first 4 values sorted, and keep doing that until we have the entire array sorted. So thinking of it this way in terms of subproblems makes the algorithm a lot more simple. Now, since we are doing it with subproblems, technically if we wanted to, we actually could solve this using recursion, which is a technique we just learned, but it's not really useful in this case, so I won't do it. We can do this without recursion, aka we can do this iteratively. We can have an iterative solution, which is using loops. Now the idea is we're going to loop through the array, but we're going to start at the second element because we know that this subarray is already sorted. So starting here and assuming that every value before this position, meaning this subarray, is already in sorted order, our goal now is to have this array be sorted. So our goal really is to figure out where to put this value. We already know all of these are sorted. Where should we put this one in terms of this array? In this case, we don't have a lot of choices. The logical thing to do is compare this value to the only other value in our array. Is this larger? If this is larger, then it should stay where it is. If it's smaller, it should be swapped with the value over here. Since this is larger, it can stay here. Now there's the other edge case where what if both?
So if the value, okay, so first thought, chain of thought is if the value is greater than preceding values, then it stays right there. Okay, that sounds good.
Both of these are equal. If that's the case, this value can also stay here because it doesn't matter whether this goes here or here if they are both equal, because it'll be sorted either way. This is for ascending order, but it would work the same way with descending order as well. So now that we know where this value should go, it should stay where it is, we can now move to the next value. So by the time we get here, we know that this subarray is already sorted. So at this point, we're going to do a similar comparison. We're going to compare this to its left neighbor. Is 4 greater than 3? Yes, it is. So it's going to stay exactly where it is. And at this point, we didn't even compare 4 to 2, but we don't need to. Do you know the reason why? Well, we already know these were in sorted order. So if 4 is greater than 3, of course it's going to be greater than every value to the left of 3 because these are sorted. Every value to the left of 3 is going to be less than or equal to 3. And now every value to the left of 4 is going to be less than or equal to 4. So at this point we know that these values are in sorted order, we can shift our pointer to the right by 1 over here, and now things are going to get a little bit interesting. So now we have this sorted portion, and we have to figure out where the 1 should go. Should it go at the end of these 3 values? Should it go in between these 2 values? Should it go in between these 2 values? Or should it go over here? Well, let's see what the algorithm does. This is why it's called insertion sort, because we're taking one value and inserting it into a sorted array. So let's see what the algorithm does in this case. First, we're going to compare 1 to 4. Is 1 greater than or equal to 4? It's not. So now we finally execute the other case. And by the way, the pseudocode for this would look something like this. Remember our pointer, which is I, in this case, started at index 1, and we're going to keep going until we've reached, the end of the list. So that's pretty straightforward. And now we're going to get to the interesting part where we compare this to the neighbor. So we have a second pointer for the neighbor. We call that j. This is at I, or you could also call this j plus 1. That's what we're going to be doing. And then you compare these. And now the value at j plus 1 is less than the value at j. That's this part of the code. This part is basically to make sure that we don't go out of bounds. And you'll see what I mean in just a second. But now that this comparison holds, we're going to perform the swap. This is where we take this value and move it over here, and take this value and move it over there. So the first thing we would do actually is take the value that was originally at j plus 1, which is 1, and put it in a temporary variable, because what we're going to do is now at this index j plus 1, we're going to move the value that was here. So we're going to put a 4 over here. And then over here, now that we've lost the 1, we have to use our temporary variable. So we're going to put a 1 over here from our temporary variable. And originally our j pointer was over here. We're going to decrement it by 1, which means we're going to shift it to the left by 1 over here. And the reason this is a while loop and not just an if statement is because now we're going to continue this whole process. We originally had the 1 over here, and we know it should be shifted to the left because it's definitely less than 4, but we don't know that we're done. We don't know that this is the final spot that this 1 is going to be. We have to continue comparing to the left neighbors. So now we're going to execute the condition again. First, we're going to make sure that j is not out of bounds yet, because as we keep shifting it, we know at some point it's going to be all the way over here. It could be out of bounds, but right now it's not out of bounds. We know that because it is greater than or equal to 0. And now we're going to compare the value at j plus 1 to j. J plus 1 is less than the value at j. 1 is less than 3. So now we're going to do the exact same thing. We're going to perform the exact same swap. So now we have our 3 over here and our 1 over here, but we're not done yet. We're going to decrement our j one more time. So now j is going to be over here. It's still in bounds. And the value at j plus 1 is again less than the value at j. So now we're going to do another swap. So the 2 is over here and the 1 is going to be over here. And now j is going to be shifted to the left by 1 again. Now it's out of bounds. So now there's no point in even doing a comparison. That's why we're checking that it's in bounds before we do this. We don't want an index out of bounds error. So since it's not in bounds, we can stop doing this loop. And we know now that our I pointer, by the way, was over here. So now at this point, our I pointer is going to be shifted over here because we're going to execute the next part of the for loop, the outer loop that's over here. And we know because of that, this portion of the array, these first 4 values are now in sorted order, and they look sorted as well. 1, 2, 3, 4. So now that our I pointer is over here, our j pointer is going to be initially over here. J is in bounds. So now let's compare the two values. Is 6 less than 4? It's not. So we know that this is greater than 4. Therefore, it's going to be greater than all of these as well. So that means that this is already in sorted order. Our outer for loop is now going to stop because there's no more elements over here. Characters. If we had something like B, C, A, as long as we have a way to compare characters, so in this case, let's say we're sorting based on just alphabetical order, we can basically sort any set of values as long as we have a way of comparing two values together. So in this case, we could sort these to be something like ABC. Of course, we could also sort strings themselves the same way a dictionary sorts words. So a word like apple would go before a word like banana. So this first 7 could have gone here, and then the second 7 would have gone here. Or they could have been in reverse, right? This 7 could have gone first, and then this 7 would have gone second. Both of those are valid sorting order, but a stable sorting algorithm will preserve the original order when there's a tie. We know that there's two 7s. And for some reason, if we wanted the original relative order of these two 7s to be preserved, meaning this one showed up first before this one, so it should go first in sorted order. That's called stable sorting. Unstable sorting might achieve this, but there's no guarantee. It's not necessary that that will be preserved, so it could have flipped them for some reason. We'll touch on this again as we continue, but my question for you, based on this, do you think the insertion sort algorithm is stable or is it unstable? Well, let's quickly go through how it would execute on this. First, our pointer would be over here. We would compare the 3 and the 7. They're out of order, so we would swap them. So then our first two values would look like this. So that's good so far. And then our third pointer would be over here, right? And this would be a 3 and this would be a 7. And we would say this 7, is it less than the 7 on the left of it, right? That's where this would execute. This 7 is not less than that, so it's going to stay exactly where it is. So therefore, we would achieve this output where the relative order in case of a tie would be preserved. These two would stay in the order they were in originally. So based on this implementation, this is a stable sorting algorithm. It's preferred to keep an algorithm stable if you can. We could code this in such a way where it's not stable, but that would have no benefit for us. So we're going to keep it insertion sort algorithm do. Well, we would have a pointer over here. We would want to, of course, iterate through the array, but then we would do a comparison. From here, we would compare it to the left neighbor. They're already in sorted order, so we don't have to do anything. We can shift our pointer over here. We compare these two values. They're already sorted. We don't have to do anything. We shift the pointer again. Then we compare these two values. They're already sorted. We don't do anything. We shift the pointer. We're out of bounds. That means we're done. So as you can see, when we have an array that's already sorted, we run insertion sort, and the execution is just iterating through the list, which is big O of n time complexity. Of course, we have nested loops here, but just because we have a loop here doesn't mean it's necessarily going to execute. I just showed you an example where this inner loop is never going to execute. So in this
Okay, that's quite weird. The best possible scenario is big O of n. You know, best possible scenario is big O of n. The worst possible scenario is big O of n squared. Um, if it's in decreasing order, 6, 5, 4, 3, 2, 1. So now this will compare. This will become 5, 6, 4, 3, 2, 1, 4, 5, 6, 3, 2, 1, 3, 4, 5, 6, 2, 1, 2, like that. Is it n square? Yes, it is n square. No, n square is n times n, but this is not n times n. This is uh, what do we call this? N plus n minus 1 plus n minus 2 plus n minus 3, that is equal to n plus n minus 1, so that is 2n minus, it's it will be 2n, so it's still n, and that's not fair. It is n. It is n.
case, the best case time complexity is big O of n. Now, technically, big O means worst case, so I'm kind of misusing it here, but it's kind of common for people to talk about it this way. But in this case, I'm saying the best case time complexity, which would occur when the input is already sorted, is going to be linear time complexity. Let's look at the other case, where is the worst case time complexity, which would actually occur on the opposite example, where the input is in reverse order and we want to sort it in ascending order. So in this case, again, we would loop through the array. We would start here. we would compare the two neighboring values. We would see that they're out of order, so then we would have to swap them. We would put the 3 over here and the 4 over here. Then we would shift our pointer over here, and then we would compare these two values, and then we would see they're out of order. We'd have to swap them again. We would have to put the 2 over here and the 4 over here. And at this point, we're still not done yet. This 2 is going to be compared to its left neighbor now, and they're again out of order, so we would have to put the 3 over here and the 2 over here. So you can see it's definitely getting messy, but ultimately what we would find is we would have to take this 3, shift it over here. Then we would get our pointer over here, this 2, we would have to shift it here, and then we would have to shift it here. Then when we get to this 1, we would have to shift it to the left, then shift it to the left again, and then shift it to the left again. So for every single value that we iterate through, the inner while loop would have to execute the maximum number of times until that value is shifted all the way to the left. When we get to the 2, we'd have to shift it all the way to the left. When we get to the 1, we'd have to shift it all the way to the left. Now for an input size of 4 in this case, n squared time complexity would look like 4 squared because the length is 4, which would be something like 4 plus 4, right? Added together, how many times? Well, 4 times. That's just the math formula here. But this isn't that. What we were doing right now was actually a bit different. What we actually have is something like 1 and then plus 2 and then plus 3 and then plus 4, because for this value we might have to consider it to be in these 2 positions. For this value it could be in these 3 positions. For this value it could be in these 4 positions, which correlates to that 4, and I just talked about the 2 and 3 case. And we might not have a 1 case because remember we're skipping the first index, but again this is just an approximation, and that's enough for us when we're doing big O time complexity. Now what most people do when they have nested loops, they automatically assume that the time complexity is big O of n squared, and usually it's the correct assumption, but I bet most people don't know why that's the case. And I'm going to explain it to you briefly right now. This equation is bounded by n squared. It's pretty obvious when you look at it like this because every term here is greater than or equal to every term here. But I'm going to show it to you in terms of big O time complexity, where remember, we know that constants don't matter when we're multiplying by a variable, right? So some constant c times n squared doesn't matter regardless of what the constant is. I'm going to use this idea to prove it to you that this is bounded by n squared, and I'm not even going to use a math proof. Now, maybe I'm not smart enough to show you the math proof of why this is true, but I'm smart enough to draw a picture, and that turns out to be enough. We know that n squared, where n is 4, would look something like this in terms of geometry, right? 4 times 4, right? This is us having to iterate through an array of size 4 times. We have to do that. We have to iterate through it once, twice, 3 times, 4 times. But we also have the case where we iterate through just, let's say, the first value of the array, and then the first 2 values of the array, and then the first 3 values of the array, and then the first 4 values of the array. So maybe now it's becoming a little more obvious why this is bounded by this. And not only that, this is actually pretty much exactly half the size of n squared. And we even talked about how the first term in this case doesn't actually apply. So maybe this isn't even there, but it's still, you can see, approximately half the size of n squared. We didn't even use a math proof to figure this out. This is obvious enough from looking at a picture. So if this is half the size of n squared, we can write it as n squared divided by 2, or in other words, 1/2 times n squared. And this is just a constant, remember, and we don't care about constants. So we can say this, or in other words, iterating through an array like this would be the same as big O of n squared time complexity. That's the worst case time complexity of insertion sort. So that was a lot to cover, but to finally wrap up, our first sorting algorithm, insertion sort, which is a stable sorting algorithm, has a worst case runtime of n squared. But it's also worth mentioning that the best case runtime is big O of n. That's not always true for other sorting algorithms, but it does turn out that there's better sorting algorithms than n squared worst time complexity. Merge sort is one of the most common sorting
Okay, so
algorithms, and for good reason. It's a pretty efficient algorithm. The main idea is to take the input array and then split it into 2 approximately equal halves. And then for those halves, split them into approximately equal halves, and then continue to split each subarray until we can't split them anymore, which would mean we have individual elements left for us to then sort. The idea is to break up the original problem of sorting the entire array into subproblems. So in order for us to sort the entire array, first we can sort the first three values, 3, 2, 4. So we can sort the first half of the values. In this case, we have an odd number of values, so we can't split it exactly into half, but more or less it's approximately half. And then the second half of values, we want to sort these as well. But then for these subarrays, we also have subproblems. We can split this array into half, the first half and the second half, and sort those portions of the array before we sort this original array. And the same thing for here. You can see that since we have a natural way of splitting this into subproblems, until of course we reach the base case where we just have subarrays of a single element, like down here as well, this problem naturally lends itself to recursion. I promised you that recursion was going to come up a lot more, and this is one of those cases. And this is clearly two-branch recursion because we're splitting this into two halves. And I'll talk later why exactly we're splitting it into halves. But to give you a hint, as you know, the number 2 is pretty important. And as we take the array and divide it by 2 each time, that lends itself to be an efficient algorithm. We'll talk about that more a little later. But this array as well is being split into two halves, two branches. This array, same thing. But these are the base cases. Now we talked about how we're going to divide this into subproblems. By the way, the technique we're using right now is sometimes called divide and conquer, because we're taking the original problem and dividing it into subproblems and then solving those subproblems before we solve the original problem. But I haven't talked about how we're even going to solve these subproblems and what we're going to do once we have that done. Well, let's start on the left side. We're going to first take this array, get the left half of it. We're going to take that and get the left half of that. And then we're going to take this and then split it into two individual elements, 3 and 2. Now this is technically a sorted array, and this is technically a sorted array. When you have two sorted arrays, we can merge these two arrays back into the original array such that they are in sorted order. That's why this is called merge sort, because we break it up into two subproblems and then merge them back together. So for getting the original values that were in the array, we create a copy of the value that was here, and we create a copy of the value that was here. And in this case, it's pretty simple because we just have two elements. So we're going to compare these two. Which one is smaller? 2 is smaller. So the 2 is going to go over here, and the 3 is going to go over here. Now from the perspective of this array, we've solved the left subproblem. We have this portion sorted. Now we need this portion sorted. Well, it's just a single element, so this is the base case. So now we don't care about the original values that were over here. We have two sorted arrays, and we want to merge them together into the original array. In general, the algorithm is going to be 2 pointers for us to do that. We're going to start at the beginning of this array, and we're going to start at the beginning of this array, and we're going to compare the values, because we know at the beginning of each array is going to be the smallest value, because this is sorted and this is sorted. So we're going to compare the two values. Which one is smaller? 2 is smaller than 4, so 2 is going to go over here. The pointer that was over here is now going to be shifted to be over here. And now we're going to continue the algorithm. We're going to compare the value here to the value here. Which one is smaller? 3 is smaller. So the next value that we insert is going to be 3 in the next position of this array. And at this point, our pointer that was in the first array is now going to be out of bounds. So at this point, we have no choice but to place the value from the second array in the next spot, which is also the last spot. So we put the 4 over here. So now we finally arrive back at the original problem we were trying to solve. We sorted the left half of the array. Now it's time for us to sort the right half. So then we have this portion. We break it up into individual elements. We don't care about what's originally here. We compare these two values. Which one is smaller? 1 is smaller than 6. So we put a 1 here. That is what the original value actually was. And we put the 6 here. So in this case, the original was already in sorted order. But we still had to do this work anyway. But now that we took the original array, have it sorted into a left half and a right half, we can merge these two portions together to make the original array sorted. So forgetting about the original values that were over here, we again use our 2-pointer technique. We have a pointer at the beginning of the left array and a pointer at the beginning of the right array. We compare the values. 1 is smaller than 2, so we're going to take the 1, put it at the beginning, and then we're going to shift the pointer that was here to be over here. By the way, we are going to have a third pointer in the output array. It's going to tell us where we should insert the next element. Originally it's over here. Now that pointer is going to be over here, and then next it's going to be over here, and then here, and then here, and keep going until, we run out of elements to insert. But right now we're going to be comparing the 2 and the 6. Which one is smaller? The 2 is smaller, so we're going to insert the 2 over here. We're going to take the pointer that was at the 2 and then shift it to the right to be over here. And we're going to repeat which one is smaller, 3 or 6. 3 is smaller, so let's put the 3 over here and then shift the pointer to be at the next element. Let's compare these two again. 4 is smaller, so we put the 4 over here and then shift our pointer to be over here now. It's out of bounds, so we have nothing left to compare this 6 to. So at this point, whether we have one element over here or maybe we would have a couple more elements over here, regardless, since we ran out of all elements of one of the arrays, at this point, we would just fill in the remaining spots from the other array that's non-empty. So in this case, we only have a 6, so we put the 6 here. But if we had more elements like a 7 and an 8, we would just start filling them over here. So taking a quick look at the code, like I said, this is going to be a recursive algorithm, clearly, where we're breaking it up into 2 steps. So this is going to be 2 branches of recursion. Now into this merge sort function, I'm passing in the starting index and the ending index as well as the array that we're actually going to be sorting. That's because as we break this up into subarrays, we don't necessarily have to create a variable for each subarray. We can just kind of keep track of this half based on the starting index and the ending index, rather than actually creating a brand new subarray like that. But how do we know if we've reached the base case? Well, if the length of the subarray is less than or equal to 1, well, how do we get the length itself? We can take the ending index minus the starting index plus 1. So basically, this element by itself is at index 0. So what we do is take the ending index, which is 0, minus the starting index, which is 0, plus 1 gives us 1. So this is of length 1. So that's how we know it's a base case. That means it's already sorted, so we can just return the array itself. But if we got to a case like this one where the starting index is 0 and the ending index is 1, then we're going to get the ending index minus the starting plus 1, which is going to give us a length of 2. That's correct. This is length 2. But that means our length is not less than or equal to 1. So what we have to do is calculate the middle index between these two. So we take the starting plus the ending and divide it by 2. So 0 plus 1 divided by 2. So most programming languages will round down. That's what we want to do, round this down. So a 1 divided by 2 is going to evaluate to be 0. So we're going to say the middle index is 0. This is the middle index. So what we're going to do now is break this up into 2 halves. We're going to call merge sort from starting to middle. So in that case, this means call merge sort on the array starting at index 0 and ending at the middle index, which is 0 as well. So we're going to call, basically that evaluates to this. We're going to call merge sort on just the first element. And we're also going to call merge sort on the second half of the array. So from index m plus 1, which is 1, and the ending index, which is also 1. So that's pretty much correct. We're going to call merge sort on this portion of the array. And these, of course, are the base case. So after we call merge sort, we're going to expect those 2 halves to be sorted. So then what we're going to do is merge those halves together. Now, I haven't shown you the implementation of this. It's not super complicated. It's just a decent amount of code. It's basically the 2-pointer technique we were talking about a moment ago. But what we're saying with this function call is merge the left half of the array, which starts at index s and ends at index m, and merge that with the right half of the array, which starts at m plus 1 and ends at index e. So it will basically merge these two together into the original 2-element array. Now I will say when we do merge the left and right half together, we do need to create extra memory. So for the left and right half array, we're going to create temporary arrays. So we are going to create copies of the left and right half arrays, but we're only doing that for the merge step. So only when we start to actually merge them together into the original are we going to create those copies so that we don't lose what the original values were. So in general, we start out with a big problem, we split it into 2 sub-problems, solve the sub-problems, and then merge the result of the sub-problems together. Now in terms of time complexity, this is a relatively efficient sorting algorithm because we're splitting it into halves. We're doing that on purpose because it does make things more efficient. So the first question is, starting with an array of length n, how many times can we split it by half? In other words, how many levels are there to this recursion? Because it's going to be the same number of times where we can take n and divide it by 2. Because here we have, let's assume actually we just had 4 elements to keep the math simple. We would have 4 elements. We would split it into 2 elements on each side, and then we would split it into one element on each side, and these two wouldn't exist. I'm doing this just for simplicity, but we start with n equals 4, we divide it by 2, so n equals 2, and then we divide it by 2 until n equals 1. We know when n equals 1, that's our base case. So what's the math formula for how many times we can take this number and divide it by 2 until it's equal to 1? Well, if we were starting at 1 and then multiplying it by 2 every single time, that would be something like 2 to the power of n. But we're doing the reverse of that. We're dividing it by n. So what we're asking is we have a number n and we want to divide it by 2 and then divide it by 2 and then divide it by 2, which is the same as saying 2 times 2 times 2, etc., right? Which is the same as saying 2 to the power of some variable like x, right? This is the number of times we're going to divide this by 2. And we want to keep dividing it by 2 until it's equal to 1. Well, by doing a little bit of algebra on this, we can rearrange this to be the same as n equals 2 to the power of x. We care about x. That's how many levels are going to be in this merge sort algorithm. So how do we solve for x? Well, in case you forgot a little bit of math, I'll tell you, we can take the log of both sides of this equation. That will give us, and by the way, I'm doing log base 2. Log base 2 of n is equal to log base 2 of 2 to the power of x. And if you forgot your log operations, this can be simplified to take this x away and put that x over here. Now, log base 2 of 2 is the same as saying 2 to the power of what is going to be equal to 2. Well, 2 to the power of 1 is equal to 2. So this whole thing, log base 2 of 2, simplifies to be 1 is what I'm getting at. So what I'm saying is we already solved for x. X is equal to log base 2 of n. So what I'm saying is if we have a number n equals 4 or any number, how many times can we divide it by 2 until it's equal to 1? Well, our answer is log base 2 of n. Log base 2 of that value is how many times we can divide it by 2 until it's equal to 1. And this turns out to be a reoccurring theme throughout algorithms and data structures. It's something we're going to see a lot more throughout the course. And this is kind of the math background of why most people don't touch on this and most people never learn it and never understand it. But I wanted to explain it to you because I think thinking about it this way and understanding your thought process is very important throughout algorithms and data structures. It's really what separates beginners from people who can solve problems on their own. So we did all that work just to figure out that the height of this is going to be log base 2 of n. I'm going to usually omit the 2. Usually it's implied that logs are base 2 most of the time. But that's not the entire time complexity. That's the number of steps that we're going to have. But what's the time complexity of each step of this algorithm? Well, it's big O of n. Let me tell you why. Basically, it has to do with this merge step. So suppose we're at this step of the recursion. We have our subproblems here, and now we want to merge them together in this array. What are we going to have to do? We're going to have to iterate through every element in each of the subarrays, which is going to result in an element being put in each spot in the original array. So basically, for this step, we're going to have to iterate through every position of the input array. So that's clearly an O of n time operation. But my argument is we're going to be doing that for every level in this recursion. So here for this subarray, we're going to split it into a couple smaller ones and then merge these into this array. But this is only half of this level, right? To do this part of the level, we're going to have to do the same thing. We have an individual element here and here. We're going to merge these together into the original array. And so this level, to build this level, took O of n. And similarly for the bottom level, it's the base case, but we still have to visit this, right? Like one operation is still going to run for this part, and then same for this and for every part of this. So this level takes O of n time complexity to construct this level. So basically the number of levels we have is log n. For each level, we're doing big O of n time complexity. So the overall time complexity becomes log n times n, or in other words, we could write it as n log n time complexity, where this is being multiplied by that. So overall, the big O time complexity of merge sort is n log n. Now the memory complexity is going to be big O of n because at any point, which is going to result in an element being put in each spot in the original array. So basically, for this step, we're going to have to iterate through every position of the input array. So we're going to split it into half of this level. Merge these together, took O of n. And similarly for the bottom level, it's the base case, but we still have every level. So basically the number of levels we have is log n. For each level, we're doing big O of n time complexity. So the overall time complexity becomes log n times n, or in other words, we could write it as n log n time complexity, where this is being multiplied by that. So overall, the big O time complexity of merge sort is n log n. Now the memory complexity is going to be big O of n, because at any point, like for this point, we're gonna have to create two temporary arrays, which are these ones, to build the original array. So that's gonna have extra memory, which is roughly big O of n, which is the size of the original input array. So now the last question to answer, is merge sort a stable sorting algorithm? Does it preserve the order of elements where there's a tie? Like, when we sort this array, will this 7 come before this 7? Well, we can definitely code it in such a way that it does. So first we'll merge these two together. There's only one way to merge them together. The 3, of course, is going to go before the 7. It's smaller. It has to do that. And this value, there's only one 7, so that's the only way we can have that. And now as we build our new output, we're going to have 2 pointers, one pointer here and one pointer here. This one is smaller, so we have no choice but to put the 3 over here. Next, we're going to shift this pointer to go at the next position. Now, to make sure that this is stable, we have to put this 7 before this 7, because now there's a tie. How are we going to code that up? We're going to say as long as the element from the left array is less than or equal to the value in the right array, then this value is going to go in the next spot. So it matters how we handle the equality case. That's the edge case. If this one is smaller, it's going to go first. If this one is smaller, it's going to go first. But if they're both equal, showed up the time complexity of worst sorting from the value and log it 1. Again, we store, and then instead of level, tation is still going to go up. So this is quicksort is another common.
Okay,
Merge sort is one of the most.
so I am on merge sort, right? 22 minutes का भी जो था. Wow. It's a hard problem. Okay, okay. Let's work it out. Python language info. Okay. You are given an array of k linked list. Each list is sorted in ascending order. Return the sorted linked list is uh, return the sorted linked list that is the result of merging all individual linked lists. Basically a merge sort. Ah, so let's say merge k sorted list. We don't have, oh, we do have to use. The lists are already merged, so that's good. The lists are already merged. Okay. The lists are already merged, so I don't have to use merge sort. Uh, Sorry, the lists are sorted. Merge the sorted list. e.g. example. Oh, sorry, where is it? Yeah. 1, 2, 4, 1, 3, 5, 3, 6. So that will become 1, 1. Let me just go on linked list. Lead code. It's better to do that. Lead code, merge, case, sorted list. You know why I'm doing this to improve my chances. Oh, it's a linked list. Okay, yeah. Okay. So now the first thing that I have to do is this is this is similar to merge sort. 1, 1, 2, 3. 1, 1, 2, 3, 4, 4, 5, 6. What I have to do is, yeah, bro, yeah. They are already merged. At a time, I'll take at a time, I'll take two. Okay. At a time, I'll take two lists, merge them, so it is still recursive. But okay, so the first thing that I have to do is I have to, let's say, okay, this will be recursive. First thought of first thought. Okay. Like, my first thought is take two lists at a time, merge them, and and do for all the lists. So the example will be recursive. Okay. Uh, should I start comparing the first and second? Start comparing the first two lists. While uh, let me just do head. Head equals to head of first equals to list of zero and zero of that. Head of second equals to list of one and zero of that. If while head of two and uh, one, right? If head of two dot val is less than if let me create yeah whew, and new equals to list number. Perfect. If head of one is less than head of two dot val new equals to new dot next equals to head one. Else new dot next equals to head two. Now uh, one, two, four, one, three, five. Then a while loop which means dot next exists, right? Dot next exists. So what I'm gonna do is okay, okay, okay. Let's just think of how I can there are two focus. One is merging and the other is recursion. Let's just focus on what matters in the process part. Okay. Instead of recursion, what I can do is I can do a for loop and create a helper function. Okay. So if while head one, head two, that means the value does exist. If head one is less than head one dot val, then new dot next equals to head one, right? Here is the new one, new, then head one. In this scenario, it will not be less than, let us do less than, so it will be stable and one is less than equal to val, so head one. So this will, let's just do now, it will be here, it will be here, just here, and head one dot head one equals to head one dot next, else head two equals to head two dot next, right? That's a good theory. In theory, what will happen is when we start the while loop, we'll first check if head one dot val is less than equal to head dot val. Yes, it is less than equal to. So new dot next equals to head one. New dot next equals to head one. And new equals to new dot next. Perfect. New equals to new dot next. That is correct. That is correct. Now, in the second loop, this one is less than, so uh, one will come here. New next हो गया. I just want to stop this. I hate this settings. Air view. I don't want air view. Air command. Okay. Once again, head one is less than head two. So new dot next equals to head one. Head one equals to head one dot new dot next equals to head one. New dot next equals to head 1 equals to head 1 dot next. And so now 3 and 4, option 2. Now, um, head 1 and head 2 is still there. 4 will join here, 3 will join here, then 4 will join here. Then the is here, 5 will join here, and will come here. Now I don't have anything. How do I change the test cases here? I don't know. Hey, it did work. Zero. My bad. 1134. Okay. So why doesn't it have two? Hmm. Oh, why doesn't it have four? Oh, because head one is there. Okay. will be work. Yeah, it did work. Perfect, perfect. Yeah, I can do it because easily. If I want to, I can just create a helper function which much easier to work with. Okay, perfect. And because it's less of zero. Now what I'll do is 1 will be 10, the other will be left of I, right? So that means for the first, when I equals to 1, the temp will be 1, 2, 4. When I equals, this is for I equals to 1. When I equals to 2, temp will be 1, 1, uh, 3, 4, 5. And the other one will be 2, 6. I equals to 2 equals to this, and temp will be this. Now what I have to do is I just have to return 10. Elif len of list equals to 1, return list else return is no creating whatever they want. I'm not sure, man. I hope it's wrong. Unexpected indent. What does it even mean? Oh, sorry, my friend. Yes, I meant to call the double exception. object of type has no length. Once again, this is also how the same. Yeah, answer one. No. Hmm. See, STD out is this. What do you even mean? Output should be a list node. Okay. How it is not a hard question. Man, I have solved it in such less time. It was easy. But the question here is, what do I do with the last one? It's just this simple one, man. Um, See, I know there is one more question that my is failing now. It will fail. It passed. Nice, 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 nice. Output is 0. What does it even mean? Output is 0. Val is not 0. Val equals to 0. Do I just do list 0? It doesn't have any. Hmm. Uh, list node val equals to null. Yeah, the output is null. Ah, dot next. Dot next. Hello. 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 Okay, this is quite fast. Return none. Oh my god. Flag to if list flag array arr dot sort. Eh? Oh my god. Dumb people. Thank you. I have done in a natural and honestly a perfect way. This doesn't look like a hard question. Okay, no worries. So let me run by things with myself once again. What I have done is dot next is none. So I just have to return none. Accepted. Okay, no worries. I'll first check whether there are more than two. Yeah, pretty fast in my opinion. Let's just mark it as pause. Yeah, mark lesson complete. Mark lesson complete. Mark lesson complete. Factorial, bro. I know what is factorial.
Quicksort is another common sorting algorithm, and it's actually very, very similar to merge sort. The idea is that instead of splitting the array into two equal halves and then sorting those halves, instead, we're going to pick a random value, and for convenience, we usually pick the rightmost value, and this is called the pivot value. So the pivot value is special because what we're going to do is we're going to iterate through every single value in the input array, except for the pivot value, so basically every value before the pivot value, and we're going to compare that value to the pivot. And every value that's less than or equal to the pivot value is going to be in the left partition of the array. So what we're going to do is take the input and partition it into two pieces, a left and right piece, where every value that's less than the pivot, less than or equal to the pivot, is going to go in the left half, and every value that's greater than the pivot is going to go in the right side. And performing this partition is actually pretty simple in terms of code. And we can actually perform the partition in place. That means we don't need to allocate any extra memory to do the partition. We can do it with just a single array. What we're going to do is take the rightmost value, that's going to be called our pivot. We're going to have a pointer that's going to start at the beginning of the array, and the idea is if we took every value that's less than or equal to the 3 and then placed them in this leftmost area, if every value in the input array that's less than or equal to 3 was placed over here, then by definition, all the values that are greater than 3 would take up the remaining spots. As long as we swap them appropriately, that's going to be the case. So all we have to worry about is taking the values less than or equal to this and then filling them starting at the left side. If we do that correctly, then the less than or equal to values will be here and the greater values will be here. So let's start doing that. So we're actually going to have two pointers. One pointer is just going to help us iterate through here, and then the second pointer is going to tell us where we should insert the next value that is less than or equal to 3. So first we get to 6. 6 is not less than or equal to 3. So in this case, we don't do anything. We take our pointer over here and then shift it to the right by 1. This pointer stays here because when we do find a value less than or equal to 3, this is the first spot we're going to put it. So now we find a 2. 2 is less than or equal to 3. So we swap 2 with whatever happens to be in this position. So we can swap these two values. 6 goes here and then 2 goes here. Now this pointer that's over here is going to be shifted over here. Now this is the next spot that we're going to insert the value that's less than or equal to 3. So next we can take this pointer and then increment it one more time. So now we're at 4. Is 4 less than or equal to 3? It's not, so we don't do anything with it. We increment our pointer one more time. We get to 1. 1 is less than or equal to 3. So that means this 1 is going to be placed where this pointer happens to be. So we'll be swapping these two, placing the 1 over here and placing the 6 over here. And then this pointer will finally reach the pivot index, and we don't really need to do anything. We basically ignore that. But at this point, our array looks something like this: 2, 1, 4, 6, 3. We wanted to partition the array such that every value less than or equal to this was on the left side, every value greater than this was on the right side. But where should we actually put this pivot itself to satisfy that? Well, this is where our pointer ended. That means our pointer is here. That means every value to the left of that is less than or equal to 3. So this is a good position to put our pivot at. So that's exactly what we're going to do with quicksort. We perform one last swap between where our left pointer is at and our pivot value. So we end with a 3 over here and a 4 in this position. So to make it more clean, after doing our partition, we have a 2, a 1, and a 3 over here, and we have a 6 and a 4 on the right partition. Now notice how the left side is not sorted and the right side isn't sorted. Just because we partitioned them does not mean they're sorted. But what is true is every value on the left is less than every value on the right. Every value on the right is greater than every value on the left. Now this is where the recursive step comes in. Now let's run quicksort on the left side and run quicksort on the right side. Now before we recursively run quicksort here and here, one thing to notice about the 3 is that it's already in sorted order. Everything to the left of it is less than or equal to it, and everything to the right of it is greater than or equal to it. So this 3 doesn't actually need to be part of our equation anymore. We can just ignore this. So it does exist, but we're not focusing on it. When we run quicksort on this subproblem, let's just focus on these two values. This is already exactly where it needs to be. And that's always going to be true of the pivot value. So now we're going to choose the rightmost element, which is going to be our pivot. So in this case, 1 is our pivot. We're going to start at the beginning of the array, we're going to compare 2 to the pivot value. Is 2 less than or equal to 1? It's not, so we don't do anything. And then we would take our pointer increment to be here. It's at the pivot, so we don't do anything. That's when we stop. And the last thing we do before we split the array is we take the pivot and swap it with wherever our left pointer would have been. Remember, our left pointer starts here, and since we didn't end up swapping anything here, our left pointer would stay here. So what we're going to do is take 1 and 2 and then swap them, because we know our pivot should go at the beginning. 1 should go at the beginning, 2 should be here. And so this is the index that our pivot went to. And I didn't mention this earlier, but when we take the array and then split it into 2 pieces, we do it based on where the pivot value was inserted. So the pivot value 3 was inserted right into the middle. That's why we took the first 3 values and then put them over here, even though we didn't actually include the last value. And then we took all values to the right of that pivot and then, ran quicksort on them over here. But so now that our pivot was over here, we're going to take the 1 and it will go on the right side, and then all the remaining values, in this case 2, are going to go here, and that's essentially the base case anyway. So when we run quicksort on this and this, we're not going to do anything. Of course, an individual element is already sorted. And remember, for quicksort, we're not allocating any extra memory. These swaps that we're doing are happening in place. That's the advantage of quicksort over a merge sort. We don't actually have to allocate extra arrays. Now, running quicksort on these 2 elements, this is going to be our pivot. This is where our pointer is going to start, and this is also where our left pointer is going to be the pointer that tells us where to insert the next element that's less than or equal to the pivot. So is 6 less than or equal to the pivot? Nope. So we take our pointer, our left pointer will stay here, but our I pointer will be incremented over here, and that's how you know we can stop when we reach the pivot. And then the pivot will always go to the position that the left pointer stopped at. It was over here, so we swap these 2 values. So this would be a 4, and then this would be a 6, and then we would run quicksort on these 2 subproblems, 4 and 6, but this is the base case. This is also the base case, so we're